So this is the last lesson on geometric sequences and series, and looking at what we call an infinite geometric series, which really just means a series that goes on forever, has an infinite number of terms. And we've actually been working with these a lot. Now keep in mind, a series is where you are adding up an infinite number of, a series in general, you're adding up a number of terms. So an infinite series, you're adding an infinite number of terms, which means one of two things can happen. Let's say your R value, your common ratio, is greater than or equal to 1. That means you're adding an infinite number of terms that keep getting larger, or if R is equal to 1, you're adding up an infinite number of terms that are the same. Well, if you're adding up an infinite number of terms that are either the same or getting larger, well, your sum just keeps getting larger and larger forever. So it never actually reaches a set number. It just keeps getting larger forever. We call that divergent, and you cannot evaluate. You cannot get a number. And it's, if it's getting larger every time, then again, you're adding numbers that just keep getting larger forever. You can never actually evaluate that. However, if you have a series where your common ratio is less than 1, or the absolute value of R, so really between 1 and -1, between there, then each term essentially keeps getting smaller and smaller and smaller. And so you can actually find a sum. We call that sort of series convergent. All the numbers, the sum converges onto a single number. And when that's the case, you can use this actually strangely simple formula to determine the infinite sum. So that formula there, which again, ideally in class, we can kind of see where it comes from. But that allows you to find the sum when you add an infinite number of values together. And it's just T1 over 1 minus R. That's it. Let's look at this series right here. And we can see the common ratio is 0.8. Every time I'm multiplying by 0.8. And so I can see this is going to be a convergent series. And so I'm just going to write here. So R equals 0.8. So this is convergent. More important than what it's called, that means I can add up all these terms forever and get a value. And I can do it quite easily. The sum of these infinite number of terms can be found by just, I'll first write down the basic formula, T1 over 1 minus R. So in this case, the first term is 10 divided by 1 minus the common ratio, which is 0.8. I should be writing down. And that's it. 10 divided by 1, subtract 0.8. And that gives you 50. So all these terms, when I add them up forever, equals 50. Now here's the idea. If I'm adding up a lot of terms, it almost equals 50. It's going to be just a little bit, in this case, just a little bit less than 50. What's a little bit? A little. I mean, it's incredibly close, but it won't exactly equal 50. It'll only exactly equal 50 when you add up an infinite number of terms, which is not really possible because infinity is not a number. So it's a weird idea what we're doing here. And this really simple formula summarizes a really strange abstract idea. You're adding up an infinite number of terms, and only when you add up all the terms do you get exactly 50. Otherwise, you're really, really close to 50. It's a really abstract idea. But in essence, as these terms keep getting smaller and smaller and smaller, after a while, these terms become insignificantly small. All right, so let me just show how this also relates back to one of the formulas we saw before. So I'll make a little note here. So note, we can imagine this as well as us trying to find, we can imagine, sorry, helps if I can speak here, that if I found term infinity, that's 0. Like after a while, so the terms get so small, so eventually if we were to get an infinite number of terms, eventually we're adding nothing every time. Since the absolute value of R is less than 1. So if we think about this formula, I'm trying to find the infinite number of terms. In fact, actually, first let me do this. Okay, so our general sort of formula for this a sum of a sequence or a series. Well, if I imagine n being infinity, infinite number of terms, well then Tn here becomes T infinity. But again, if r is less than 1, then my infinite term after a while gets closer and closer to 0. So this becomes equivalent to my first term minus r times 0. Over 1 minus r. And again, r times 0 is just 0. So in the end, this is the same as just t1 over 1 minus r. So you can kind of see how this strangely simple formula relates to what we did before. Okay, but again, a really abstract idea, probably the simplest formula you're going to be given to in this course, summarizing something really abstract and strange. All right, so for each of these series, I want to first determine if it's divergent or convergent. If it's convergent, I want to find the sum. If it's divergent, that means the sum just keeps getting infinitely larger. So first of all, is this divergent or convergent? I need to figure out the r value. And so what am I multiplying by each time? Well, let's see. I can just pick a number, 8/9, and divide by the one before it. So 8/9 divided by 2/3, which is the same as 8/9 times 3/2, which reduces to 4/3. So my r value is 4/3, which is greater than 1. And so the absolute value of r is greater than 1. Therefore, this is divergent, which means each subsequent term is getting larger than the last. And so there's no point, I can't add all these numbers up forever. It just keeps getting infinitely large. Nothing more to do. Let's look at this one. What's my r value? Well, I can just see every time I'm multiplying by -1. So in this case, the absolute value of r equals 1. But that still makes it divergent. To be convergent, the absolute value of r has to be less than 1, or r has to be between 1 and -1, not exactly equal to 1 or -1. In essence, if you add these up forever, if I add the first two terms, you get 0, then it's -1, now it's 0 again, now it's -1, then it's 0 again. And do that forever, it'll never actually converge on a number. It never comes to a set number, it just keeps changing in this case. Okay, let's look at this one. Let's find my r value. I can just see it's going to be 9 divided by -10, which is -0.9. So that's my common ratio. So I now know this is going to be convergent because the absolute value of r is less than 1, or actually I'll say the absolute value of -0.9. So this is convergent. So I can actually find the sum of all these infinite values, and I can find it quite quickly. The sum of the infinite number of values is going to be the first term, -10 divided by 1 minus the common ratio, which is -0.9. Now, I'm trying to be a little careful with that double negative down there. So it's equivalent to -10 divided by 1 plus 0.9, which is, as a fraction, -100 over 19. Or, maybe I'll do one step before that. I get -10 over 1.9, multiply the top and bottom by +10, and that's how you get to this fraction. Or you can decimalize it, but again, that is the answer as an improper fraction in lowest terms. All right, so what about this? Sigma notation, what does this mean? It's hard to really know. So let's first see it's hard to mean if this is divergent or convergent just yet. Let's think about the series here. So I'm starting from 4 forever. So I know it's an infinite series, but is it convergent or divergent? Let's look at the first term. The first term is going to be 2 to the -4. Plus the second term is going to be 2 to the -5. Plus 2 to the -6, and so on, forever. So what does 2 to the -4 mean? That's the same as 1 over 2 to the +4, or 1 over 16. 2 to the -5 means 1 over 2 to the +5, or 1/32. So this is going to be the same, again, as 1 over 2 to the power of 6, or 1 over 64, and so on. So hopefully now it's becoming clear that these are getting smaller every time. My terms are getting smaller. My r value is exactly 1/2. So this is convergent. All right, so if it's convergent, I can now find the sum of the infinite number of terms. The first term is 1/16 over 1 minus a half, which is 1/16 divided by a half. And then 1/16 divided by a half, same as 1/16 times 2 over 1. So 2/16 or 1/8. Again, nothing wrong with using a calculator, but also that was pretty fast. So notice for this, for me to see what was going on with this sigma notation, I first probably wanted to write it out as the actual series to get a sense about what was happening here. All right. Oh, the darn fractal again. So we've seen this fractal before. This time my question is a bit different. I said, say the area of this whole triangle is 1 unit, 1 square unit. So what I want to ask is, okay, what's the area of all the shaded regions in all the figures? Keep in mind, there's 3 here, but this actually goes forever. It says the first 3 figures are shown, but these, this fractal can continue step after step after step. So I want to know what is the total area of all the shaded regions in all the triangles. Because keep in mind, these just keep going forever and ever. How can we do that? Well, if I'm going to ask you to do that, somehow it has to come back to a geometric sequence, and it has to be convergent. Otherwise, I can't actually add up the total area. It'll become infinitely large. So let's see. First, if each of these triangles, come back here. If all of this inside is an area of 1 unit, then the area of the shaded part of this first is just 3 out of 4. I can literally see 3 out of the 4 of these triangles are shaded. Okay, so that's the area of that. So what's the area of this part? Well, here, if I look at all of these, I can see there are 9 shaded triangles out of, if I make them all the same, if I count them all, there's 16 triangles altogether, so 9 out of 16. So now I can see the common ratio. To go from 3/4 to 9/16, I have to multiply the numerator by 3 and the denominator by 4. And you'll see the same thing works. Or for this, if I multiply 9/16 by 3/4, I get 27 over 49. Sorry, over 48. And while I'm not actually going to count them all out, if you were to break all this up into the same size triangles, like I'm starting to do right here, you would see there are 48 triangles in total, and 27 of them are shaded. But I don't need to do all that because I can already see the sort of sequence. Okay, so now what I essentially want to do is I want to add up 3/4 plus 9/16 plus 27 48ths, on and on and on and on forever. Well, 3/4 is less than 1. I can see it's a common ratio of less than 1. So now the hardest part is definitely done. So the sum of the infinite number of terms is going to be the first term divided by 1 minus the common ratio. There we go. And again, I actually have a pretty pleasant fraction to deal with. This is 3/4 divided by 1/4, right? 1 minus 3/4 is a quarter, which is 3/4 times 4 over 1. 4's cancel out. It's just 3 whole. So if I was to continue this fractal forever and add up all the shaded parts forever, the area of that would be exactly the same as 3 whole triangles. Again, abstract, weird ideas, but my calculations are actually quite pleasant here. The hardest part, I think for sure, was getting it to this series right here. All right, the last problem. Another fractal. This is called a fractal tree. And so if we look at this tree, first let me kind of zoom in here, and I'll read what's generally happening here. So in this fractal, the trunk is 10 centimeters long. So here's the trunk. So from here to here is 10 centimeters. Okay, after that, this branch, you can think of the trunk as being the first branch. It breaks into 2. Each of those are 60% the length of the first. So each of these here is 60% the length of, in this case, 10 centimeters. Then each of those breaks into 2 trunks, or 2 branches, I should say. Each of those is 60% the length of here, and it goes on and on forever. Okay, a fractal is a geometric pattern, a visual pattern that can go on forever. Okay, what you see here are the first 11 stages of the fractal. and where the trunk is stage 1. These are stage 2, stage 3, 4, 5, 6, all the way to 11. So what you're actually seeing here is the first 11 stages of this fractal. So that's the setup. Everything I did is just read out what you have in words here. So now I want the total length of all the lines on this image shown. Okay, so what is the total length of all the lines here? Well, clearly, there's a lot of lines. So I want to connect this back to a series. I need to think what the series is. And my first term, I think, is fairly clearly 10 centimeters. That's my first term. Plus, what's my second term? Well, each of these is 60% of 10. So 60% of 10 is 6 centimeters. Okay, but there's 2 of them. So my second stage of this fractal, or the second term in my geometric series, is not 6. It's 6 plus 6, because this stage has 2 branches in it. So 6 times 2. So it's 12. My second stage is 12 centimeters. So first 10 centimeters plus 12, and that's the hardest part done. Now let's look at my third stage. There's 4 branches. Each of them is the same. Each is 60% of 6. 60% of 6 is 3.6. So each of these is 3.6 centimeters. 3.6 times 4 is 14.4. And so on, but not forever. I want to do 11 terms. Okay? Now the hardest part of the question is definitely done. Realizing, for example, the second stage is 12, not 6. The third stage is 14.4, not 3.6. If you, for example, if you think of the first stage as being 10, the second stage being just 6, the third stage being just 3.6, then in the end, you're going to be finding the length of these lines right there. One little path, but not all of them. Right? Obviously, that's going to be way less than what I want. I want all the lines. So if you don't take into account that each time there's double the branches, I'm going to end up finding the sum of just that one distance I've kind of traced out in orange. All right, now the hardest part of the question is for sure done. What's my common ratio? I can just see from here to here, it's times 1.2. 120%, which makes sense, 60% plus 60%. And now, this time though, I don't want all the branches added up. I just want the first 11. So the sum of the first 11 terms will be the first term, 10. Actually, I'll use this formula. Times 1 minus the common ratio, which is 1.2, to the power of 11, all divided by 1 minus the common ratio. Again, I'm not asking for a infinite number of terms, at least yet. I'm asking for the first 11 that you can see here. All right, that's it. If I just type this into a calculator at this point, I get about 321.5. So about 321.5 centimeters, which means if that first line really is 10 centimeters, then all the lines you see here add up to over 3 meters in length. All right, that said, that's, I think, the hardest part. But now the last question brings back to an infinite series. So assume the fractal continues forever for an infinite number of stages. If it is possible to determine a sum for the total length of all these lines, then do so. If not, explain why there's not. And so at this point, it is definitely not possible for me to get a sum of an infinite number of stages, because again, what you see here is 11, and that's because my common ratio is more than 1. Which means if this fractal really were to go forever, the lines would just, there would always be more and more each time, and it would just, the total length would just keep getting larger and larger forever. And so this is because right here, this is a divergent series, which is easy to miss. I'll just say it is not possible to find an infinite sum. It's because it's a divergent series. That said, I also have one more thing. If it is not possible, which we now know, determine a way so that the pattern can be changed so that there would be a finite sum. So how could I change this pattern here of the fractal so there would be a finite sum for an infinite number of branches? The key is I have to adjust that percentage there. I have to make it shorter. How much shorter? Well, again, every time let's say I make it 55%. but then there's going to be 2 branches. So times 2, that's 110%. So it's still too much. I have to shrink this down so that it's less than 50%. Anything less than 50%, even though I'm doubling the number of branches, it'll end up being a divergent series. So again, say this was 45%. Each of the lines was 45% the length of the previous one. Yeah, there's 2 of them. So 45% times 2 is 90%, which is 0.9 the R value would be, which would be divergent. And so in the end, let me just basically write down what I just said out loud. To make this, to make convergent, R has to be just less than 50%, or R has to be less than 0.5. And then you can actually find an infinite number of, the total length of an infinite number of stages. All right, so with that said, that ends this first part on geometric sequences and series, which then leads us into exponential functions, which is kind of the same thing. That's it.